Okay, good morning. Thank you everybody for coming along today. Just a quick overview of what we're going to be doing today. We're going to have a demo of a new Python SDK for Argo Workflows from Flavio Varden shortly. I think that's pretty interesting. We know we've got a lot of Python users. And then we're going to have a presentation and demo on LitmusChaos from Shomi and Karthik, and then an opportunity to kind of ask any questions or discuss any other topics that you would like to discuss today. If you can add yourself to the attendees list, that would be awesome. That would be really good. For people who are new to this meeting, we tend to talk about Argo Workflows and Argo events. We tend to have people come along and demonstrate those two products. I won't tell you any more about those because I'm sure you're familiar what they are. Who are we? Who runs these meetings? I'm Alex. I am a principal software engineer on Argo Workflows and Argo events. I used to work on Argo CD as well. During this, if you want to ask any questions, feel free to ask. Typically, we have like a Q&A at the end of any kind of demo or presentation. That's a great opportunity to ask them. And if you want to come back and ask any questions afterwards, something that kind of slipped your mind at the time, then obviously you can come and ask those same questions on Slack. That's fine. We are recording this, so if you want to share it with some colleagues, the recording typically goes up on YouTube the next day, sometimes 2 days, and then you can share that out. Just a quick announcement. So we've just started 3 weeks ago running a kind of a weekly meeting at Tuesday at the same time, 10 a.m. Pacific Standard Time, which is kind of an opportunity to kind of learn what people are working on right now and learn a bit about kind of what milestones and roadmaps we're doing. That's kind of aimed at code contributors. So anybody working on actual code contributions at the moment, if you're doing that. And we also talk about things like roadmap and what the future will be for Argo Workflows and Argo events, and also for data flow as well. Okay, so Flavio, are you ready?
I am.
Cool. I will let you take over and I'll stop sharing my screen.
Sounds good. Take it you can see it. Okay, there we go. Hi, everyone. My name is Flavio. I'm a software engineer at Dyna Therapeutics. And today I'm going to be talking to you about what I like to call the missing Argo Workflows Python SDK. It's called Hera, and the main intent is to make it easy for scientists in particular to adopt and use Argo Workflows by providing them with a very easy to use interface for constructing and submitting Argo Workflows. I'll talk a bit about Dyno. We are a biotech company in Cambridge, Massachusetts, and we focus on building viruses that are transfer mechanisms for delivering genetic therapies. And we have two main groups at the company. We have a laboratory and we have the computational group. Our computational group is composed of scientists and engineers. And our scientists work on numerous algorithms that are typically run in workflows for running things like model training in this realm of machine learning, or computational biology workflows that take data from the laboratory and they apply specific processes to that data. And we've used, for organizing and scheduling and submitting these workflows, we've used multiple platforms in the past. The one that was predominantly used when I first joined was Kubeflow. And of course, we used it for notebook hosting, but we also used the Kubeflow DSL. And for the majority of our scientists, it was very, very challenging to debug the workflows that they were scheduling. And it was mostly because of the way the cluster was set up, and observability was pretty challenging for them to understand. And in addition, the syntax and the vocabulary that's adopted by the KFDSL is not very welcoming for numerous, probably for the academic community. And that made it very challenging to set up things like parallelism because of the way Kubeflow will extract the variables from the payload that it receives in order for scheduling a parallel workflow. So once we moved away from Kubeflow, we adopted Argo, and then we used at first the Argo Workflows DSL to schedule to restructure and schedule some of the workflows that we wanted to submit. And it was great at the start. It allowed us to obtain almost instant value from Argo Workflows. But again, we faced numerous challenges, and it's not most of the engineering group, but it's our scientists who didn't feel empowered to build these workflows on their own for numerous reasons. But I think primarily it was because this DSL exposes a lot of the objects that come from the Argo workflow, the Python client that uses the open API schemas, if I'm correct. And you also have to write this very specific syntax to obtain input parameters and whatnot. And all of a sudden now our scientists need to know a lot of elements about Argo in order to construct and submit a workflow. In addition, it makes it challenging to easily skip steps, which is often something that our scientists want to do during their experiments. And lastly, it makes it very challenging to request specialized resources such as GPUs, because you need to essentially write your own internal library that wraps the workflow object that comes from this SDK in order to access specific fields on it, set up node selectors, set up the whatever NVIDIA card you want, and things like that. The second SDK we tried was Cooler, and it solved some of the DSL problems we had before. It is certainly more Pythonic, but inputs are still a problem. I've in the past submitted an issue mentioning this because we were using environment variables for the container, but again, you still need that very specific syntax, and a lot of the workflow setup is quite confusing for a lot of our contributors. In addition, the last time we used it, you couldn't submit to a custom domain. We have an Argo server running deployed to Kubernetes, and it sits behind an IAP. So there's a specific domain we need to hit to reach the server. And for running Cooler, you specifically need kubectl to access the Kubernetes deployment. And this is a big no-go for Dino, mainly because for practical reasons and also from a security standpoint. We primarily don't want our scientists to have to worry about these engineering tools such as kubectl in order to port forward and things like that, which conceptually doesn't sound that challenging, but the value for our company is in the scientific pursuit, not in the use of kubectl for submitting workflows. So we thought of building our own internal SDK with simplicity at its core, and we had specific requirements for that. We wanted to easily understand dependencies. We wanted an easy way to set up parallelism over whatever jobs we want to submit. We wanted to submit it easily. We wanted to maintain some high-level Argo vocabulary to maintain consistency with the Argo UI, for example, because there's a lot of value in using the UI for our scientists for debugging purposes. We wanted to support Pydantic schemas because they're easily JSON serializable, and it fits nicely with the built-in Python JSON package. We wanted quarks, and we wanted to support any primitive type like strings, integers, and things like that, because again, they're easily serializable. And lastly, we wanted dynamic fan-out because for a lot of our computational biology workflows, it so happens that we don't know ahead of time how many biological samples we're going to process and things like that. So we wanted to fetch them from somewhere and then in a single step, and then we wanted multiple parallel steps to follow up to process each of those samples independently. With that, I'll switch my screen and offer some brief demos. And a task and a workflow are primary citizens of Hera, and we have this concept of a workflow service. And the workflow service is a wrapper around the workflow service API that simply just sets the right configuration for you to submit your workflow to your own domain under the assumption that you're able to provide a bearer token to pass authentication for workflow submission. Then you inject your service into a workflow that takes currently a name, this workflow service for submission, and a parallelism element that's currently set to 50. And then you build your task. And all we're adding here is a function that's callable. And this is a very simple toy example, of course, but you can imagine our scientists building something a bit more complex as this unit as this atomic unit of execution that were submitted to Argo for execution. So they get now, they now get, our clients or our scientists now have the opportunity to exclusively focus on the implementation of the scientific code with a very simple interface for workflow submission. So again, they build the task, they add their task to the workflow, and they submit. And I'm going to spare you from having, looking at the UI pod initialization and things like that. And I just took a very simple screenshot for this example. The next one I wanted to show you is the classic diamond that is offered in the SDK examples. And again, you set up your workflow service, you make a workflow, and then you get to focus on your tasks. So you'll notice that in this case, now we have a parameter that we pass in. And the way you perform this mapping is you pass in this dictionary payload that says map message to this thing, and then it's just going to get it. And it'll execute, and it'll have that parameter for you, and it'll execute this the print statement. The way you set dependencies is you say task.next this other task. So in our case, we have A next B, A next C, B next D, C next D, and that's gonna give us the diamond. And you can also use the right shift operator, and I'll have an example of that as well. Again, you add your tasks, submit your workflow, and you're done. And I have that scheduled, a screenshot of that here. For the dynamic fanout part, we've introduced this input from concept that takes a task name. So in our case, we have a generate and a consume task. So it depends on the generate task, and it takes the value parameter that's extracted from the JSON payload that comes from the generate task. And we resorted to a simple JSON down to sys.standard out for now. Perhaps in the past, we're going to have something that looks a bit more friendly, but this is sufficiently easy to understand, and we've added a lot of documentation around this. So again, generate.next consume, add your tasks, submit, and then it looks like that, essentially. And we've also added retries that has a duration and a max duration, and that's just a simple function that says, generate a number between 0 and 1. If it's less than 0.5, raise an exception, otherwise it's success. And in this case, it tried twice when I tried it. And as the last example, that's a bit more complex, I have a task A that takes multiple messages now. And this is how you set parallelism. You say, process this input and then process this this input and this other input. And then the task will just execute in a parallel fashion. It'll make a task group for you, and it'll execute all of those, the function that you submit using those specific inputs. And I made some linear tasks as well, just for the purposes of illustration. And again, you make your dependency chain. You say A, B, B1, whatever, all the way to D. You add all of your tasks. You could have put them in a list and then start the list, of course. But this is just a simple, and then you submit your workflow, and you end up with something like this. And it's overall quite easy to understand conceptually what a task does, especially when you're using things like default parameters and whatnot. So currently, what it does, it has a lot of options that come with defaults. So it uses the Python 3.7 image, for instance. So if you don't have internal dependencies, you can just use this one. But if you have at Dino, for instance, we have a lot of custom code. So we inject our own images into this image field, and then we execute whatever code we want to submit to Argo using that specific image. It has a command field for supporting things like if you want to run the Argo script in parallel using some product like Horovod, for instance. We use Horovod for distributed GPU training, and we use a Horovod run command to launch the Argo script whenever the pod starts up. You can pass in environment variables, and there's this concept of resources that you can say, I want whatever, min CPU, max CPU, GPUs, a volume, existing volumes, and empty directory volumes. And the reason we introduced Pydantic is because you can build schema validations, which are quite nice, especially if you apply business logic into your workflow submission process. It also has tolerations and node selectors. And the reason we resorted to using node selectors and toleration is because of differences between GKE, EKS, and Azure AKE, I think, to provide the opportunity to use Hera in the context of, really irrespective of the platform the cloud provider that you have that runs your Kubernetes cluster, so that you can do things like request specific GPUs using very particular node selectors that you're using. However, I also wrote a very simple example that allows you that showcases how you can write your own wrapper to simplify submission even more. So you don't really need the service, because like your company will probably have a single way of generating the token. Your company will probably have a single domain for your Argo server. So you can imagine building your own, my workflow service that's a wrapper around your workflow service with a consistent domain and a simple way to generate your token. That's just have a mock here. And however, whatever parallelism you want to put in. Similarly, you can have very specific tasks for specific domain at your company that use maybe very specific images that are only allowed to take in specific functions or have default retries and whatnot. In our case, where we use the Google Kubernetes engine, so we know that there's this label on the nodes that have NVIDIA K80s on them, for example, and we just have this default as the default node selector for accessing K80 GPUs. Or if you have specific commands, environment variables that you want to inject, or volumes or something like that, you can write your own. And that, it just simplifies your workflow submission interface even more. It saves a single line, but at least you're saving your colleagues from the need to have these, write these details themselves. So it's currently, we currently have a repository under Argo Labs named Hera, and I'm thinking about using Hera Workflows as the pipeline name, perhaps. And I have a note here to remove the contextual elements, but they have already been removed. And what I mean by contextual elements is anything specific to Dino, because it is ultimately an internal SDK. And again, very open to feedback around the execution model, the scheduling, and things like that. Are there any questions?
Hi, Flavio. This is great, and I'm glad you've tried all the existing solutions before diving into this this new solution. Some quick questions. So when you mentioned KF DSL, do you mean Kubeflow Pipelines DSL?
Yes, yeah, exactly.
Okay, and could you elaborate a little bit why and what your data science team needs from kubectl? Since you mentioned you still need kubectl to work around with workflows submitted via Kuli, right?
Mm-hmm.
Since Kuli already provides things like status checking, and I wonder what else your team needs.
So to submit workflows to Cooler, I believe you need access to the deployment.
Yeah.
And that's why you need kubectl.
Yeah.
So you need your Kubernetes configuration to be set in such a way that Cooler can use it for submitting the workflow. And that's where the problem comes in, because we do not want our scientists to have to worry about these types of things, about having the right context, the right namespace, the right, whatever, for submitting their workflows.
Okay, got it. Yeah, since from my experience, they usually just submitted the workflows, that's it, and then they look at the UI for logs and status and everything without having to use kubectl at all. But you mentioned namespace, maybe that's something can be pre-configured instead. Yeah.
Mm-hmm. So for observability, I just want to clarify that they were definitely going to the UI. Is just the submission part that was problematic for us.
Okay. And could you go back to your demo Python script? I just want to take another look at the Python function that you imported as a step. So how do you import a module inside the say function? Are you like just using the script template directly, or do you also wrap around a little bit to make it more Python friendly?
Are you referring to how this is set?
So I'm just wondering, could you go to maybe another example where you have an import statement inside your function?
An input statement.
Maybe diamond example? Or...
This ones?
Oh yeah. So in order to use the function called generate as a step, are you just using the script template from Argo Workflows directly?
Exactly.
Okay.
Yeah. So all of this stuff is inside a script template, and whatever types your parameters have, it'll import, for example, JSON, and it'll serialize your value, and then import. So this import JSON is actually, there's two JSONs in this script if you look at it, because there's an import JSON that's automatically added in order for the script to add something like message, input the parameters X, and then it'll JSON downloads that actually. So this is automatically handled by the task. So you don't have to worry about serializing and deserializing your parameters. You can just use them. And if you use things like PyCharm and whatnot, it makes writing code much more pleasant.
Okay, got it. Thanks. This is very helpful, and I'm happy to chat further with you maybe after the meeting, since I've been working on the Kuli project and was involved in the Kubeflow pipelines as well. Thanks for the demo.
Yeah, absolutely. Jesse asked, could Workflow Service also work with Kate's API? Probably. Yeah. I think so. I don't see why not. And I think that's, I take your question, Jesse, as can we use the deployment the same way Cooler does? And yes, absolutely. Your second question, Jesse, about how does the code become what's executed inside the container, that's similar to what Terry just asked. And yes, it is via script templates. Aya mentioned that the Hera Workflows repository looks empty right now. Yes, that is correct. I'm currently working with Bala and Alex to gain access to that repository. And I do have an Argo Project Labs community issue submitted to gain access to that repository, essentially. No problem.
Do you anticipate you'll run into like the size limit of stuffing everything into the script template, especially if you have like a lot of functions or long functions? And then what do you think the mitigation for that should be?
Yeah, this is certainly a concern, and I can share from personal experience that we have some scripts specifically for training machine learning models that are quite long. And if we schedule, things that are in the thousands, then we start encountering problems. The easiest way that we found around it right now is to submit multiple workflows. It's quite easy to do that because Hera presents a very accessible interface for programmatic submission. And yeah, we just wrap tasks in different we inject tasks in different workflows, and we just execute them in a different one separately. But we've also been aiming to just refactor code as much as possible, and isolate components and put them into classes or something like that, so that the container provides those dependencies, and we make the script as short as possible. Because technically, you can just have a single function call in it, and then all of your code is actually provided by the container. So your script is no longer limited by that size. And then, of course, when you have a single line, you can go and submit 10,000, 20,000 parallel jobs or more, I guess.
Yeah, that's a good point. I think if your functions are getting longer and longer, it's a kind of a smell that you want to maybe factor that into a library instead. So
yeah, the reason we like using it this way is because it helps us iterate very, very quick. So the script template is added, sorry, the function that you submit is added to the script template as is. And as long as your container provides the right dependencies, you don't have to rebuild your image. In the case when you change your ML code, for example, in a library, you have to rebuild your Docker image, because now you're going to use a one that's out of date. So if you want quick experiments, build your script as using whatever practices you want. But then when you want to productionize it, that's maybe when you want to consider putting it into a library.
So just the technical question. So did you use like Python inspection to get the source code of the file that to get this, and then you take that and then you translate that to the, I'm just curious how that technically works.
Yeah, of course. So there's a part that looks through the arguments that are set. These are just v1 alpha arguments, and these are structured from obtained from parameters. So yes, you're right. There's a lot of inspect on it, and I'll show you the script itself. Yeah, there's a it looks for the start token. It grabs every single line and then dedents it. Does another dedent that I don't remember the reason why, but I can probably look into it.
Mm-hmm.
And yeah, that you basically guessed it right. Yeah.
Yeah. Okay, that's really cool.
In Dataflow, we do something quite similar to this, but I think the requirement is the function's got a specific name. It'd be nice to remove that requirement. I had a question. I guess this is probably for both Flavio and Terry. What about requirements.txt? What if I've got some dependencies brought in by that? Do I just need to have a pre-baked image to deal with that?
Yeah, you do need that image. Yeah, and that's why I mentioned. Sorry, go ahead.
Is that a difficult process for people, or is it typically they just have a big image with all the dependencies they'll ever want, and they just use that?
It's typically the second one. That is the preferred way of going about it, because we build it once and then it gets cached on the node, and it's very quick to use it afterwards.
Yeah, everybody's using the same image presumably in the okay, interesting.
Mm-hmm. Exactly. Yeah.
In my experience, if you have a pretty mature DevOps team, there's usually a tool available that helps data science teams build the images directly. So usually, I don't think image building is a pain point for them, but the more user-friendly, the better, I guess.
Yeah, I've been wondering if there's like an intermediate between pre-baked images and one that kind of will bring in your requirements, but I think that's probably not the case, because either you've got pre-baked image that you're happy to use, or it's been operationalized by your ops team, and it's not really a problem.
I have another question regarding the secret, because I'm trying to compare the product with Airflow. A lot of times I'm doing that. Airflow have this baked in the secret management, basically injected. So how we handle here, like, do you creating the secrets on the fly and reference it, or do you just like parsing as a string as an environment variable?
So there are multiple ways we can go about this. There's a base environment specification that will make an envar for you, and there's also a secret env specification that will take in a secret name and a secret key from a very specific secret that's currently available in a Kubernetes cluster. And I believe there are different, other kinds of secrets we could include, like the ones that pull metadata from the pod definition, but we haven't found a clear use case for that. And you can think of Hera as a stripped down version of Argo that focuses on the things that most data science practitioner will need. And in time, we're probably going to be expanding it as these use cases come up.
Okay, so basically you don't handle it. So the data scientists assuming the secrets is there, so they can connect to the data store, whatever they needed in this way. I kind of like trying to connect the dot is how data scientists in your team like doing the local development, then they transition to be like in this way. Oh, is this can run locally without any problem?
So one of the biggest advantages of being able to write these functions independently of your task is that now you can write tests for this. You can do whatever you want with that function. It's just, I can literally import it from here and write tests for it. You can write your function in a different file. You can have a task, you can have a file just with tasks and one with workflows, and then you can share these tasks perhaps and things like that. So yeah, if you write something that runs this on local, yeah, you can absolutely test it.
So I want maybe just like I'm general, don't know much about data scientists. That's why I'm asking some dummy question. Is what's the common development like process? Like I know the data scientists normally they are more focused on algorithms, so they don't care about normally, I'm not saying all of them, they don't care about the runtime.
Yeah.
So do you see that the data scientist will hand over the Jupyter notebook or something to you or to your team? Like then you help to reorganize their script and make it like production ready, like turn this in format? Or do you see they actually feel comfortable to do this themselves right now?
I see use cases all over the map. The idea of Hera is to empower scientists to run these workflows themselves. And I have colleagues who build software in a notebook, then use Hera to submit whatever software they created to Argo. And they measure metrics, performance, whatever they need, and then based on the experiments, they will adjust their code and ultimately productionize it themselves into a workflow.
Okay, thank you. This is great work.
Yeah, no problem.
Cool. Flavio, thank you very much for that. I think you've got to run off to a meeting. So any more questions, obviously just jump into the Slack channel and ask about this. I think this is kind of really interesting discussion to have about it. Okay, Shomar, Kalpik, are you guys ready?
Yes.
Brilliant.
I hope I'm audible. Yeah.
So take it away.
Screen. Okay, I hope my screen is visible too. So, hi everyone. This is Karthik and I'm joined by Shomo. We're maintainers of the CNCF sandbox project called LitmusChaos, which is a cloud native chaos engineering project. And we've been using Argo Workflows underneath the Litmus platform, as part of the Litmus platform to run complex chaos scenarios. We just want to talk about how that came about and what we're planning to do, what's going on right now in the community, and what we're planning to do going ahead in the next few months near term. We'll just do a very quick background on what chaos engineering is, what LitmusChaos is about, and a bit of history on how and why we embraced Argo Workflows and how Argo Workflows are being used today in the platform, and what changes have been made over the standard vanilla Argo Workflows. So we will be doing a very quick demonstration of Argo Workflows being executed as part of Litmus, and it will then take some questions. I'm sure all of you have heard of chaos engineering. Most of you might even be practicing it. It's basically popularized by Netflix about a decade ago, and you can see some standard definitions here. It's about injecting faults, controlled faults, identifying weaknesses in your system through fault injection. And the idea of chaos engineering is to inject these faults in a random way, unpredictable way. And there's also a lot of paradigm shift in the recent times around how chaos engineering is being practiced. Originally, it was always being done in production, but the practice nowadays is to do it a lot in pre-prod environments, especially with the advent of Kubernetes. A lot of people are re-architecting their applications to microservices model, and they're not really ready to go and do chaos engineering in their prod. It's being done as part of staging environments or CI/CD pipelines, etc. So this is a simpler definition of chaos engineering, something that we can all connect to in the current times. Just like a vaccine, and we inject harm willfully, inject failures. It could be node failures, maybe go fill your disks, do packet drops, cause CPU or memory exhaustion on your pods and nodes, etc. So this is basically something that we would try to do as part of fault injection. And chaos engineering is a lot about injecting fault with a hypothesis around how your system should behave when the fault is injected. So you might want to know how the deviation is seen in steady state. So you have an idea of how the system should behave, what we call as a steady state. And then you inject the fault, and then you see some deviation there. Maybe you expect some deviation to happen, and that is under limit. Sometimes you don't expect any kind of deviation. You expect the system to work as they are. And you might have a lot of other factors that you would want to validate as part of an experiment. Things like mean time to detection of a fault, how quickly your observability systems are throwing up your issues, or sometimes about recovery, mean time to recovery, etc. So these are all things you would like to validate as part of an experiment. So chaos engineering basically is like vaccine. And one of the reasons why we got this cloud native tag attached to chaos engineering, chaos engineering is being there for a decade now. And we added this subcategory, especially because of the way the community was looking at chaos in the Kubernetes world. And this pyramid here basically talks about the way your services are deployed in a typical Kubernetes environment. You have your platform services, you have the Kubernetes control plane, Kubernetes services. You're pulling a lot of tooling from the CNCF landscape, service discovery, storage, observability. Then you have your direct application dependencies, message queues, databases, and then your apps. And it's possible that failures can happen anywhere. And if you add to the fact that most of these components are getting constantly upgraded on your clusters, the whole practice of DevOps is about releasing fast. So you basically have a lot of change that gets injected into your deployments, into your deployment environment. And you would really want to check what's happening at your cluster. When one of these components is failing, you might want to repeat those tests over a period of time regularly. So this is about why chaos engineering is needed and how it is really more important in the cloud native world. And the other aspect, the practical aspect to cloud native chaos engineering is a lot of people today that are dealing with Kubernetes are used to a certain way of describing their applications or carrying out the regular tasks. Everything is declarative. It is all in a YAML file. It is all stored in a Git repository. It's GitOps controlled. You have resources and resource controllers. That is the way you basically go about doing things in a day-to-day Kubernetes world. So we wanted to basically do chaos engineering the same way. Chaos engineering, when I say the same way, when you're describing the chaos intent, this is the fault you want to do. This is how you want to do it. And when you're trying to add some steady state validation intent, you wanted to be able to do it in a declarative fashion and do it in a Kubernetes native way, keep it homogeneous, let the developers and SREs have the same experience with resilience testing and chaos engineering that they have with other things that they do on the clusters. That's when the Litmus project was born. So typically the chaos experimentation process has this flow. You identify steady state conditions for your infra or for your services. You introduce a fault. You check whether the SLOs continue to be met. If they are, then it's resilient to this fault. You go on to the next scenario. If not, you found a weakness, you go back and fix either the application business logic, or maybe you fix the deployment or something on the platform. You basically go adopt some better practices in terms of deployment or tuning your infrastructure. to ensure that you are going to be more tolerant to this fault. And for these particular aspects in this flow, for these blocks, we tried and came up with some custom resources. So there's a custom resource that describes a fault, and there's a custom resource that basically applies this fault on some service running on your system. There's an operator that watches these CRs and launches some runners to carry out the fault business logic. And the result of this experiment is stored in another CR. They have been kept in separate resources because there's a lot of scope, rich scope for improvement in terms of definition of these processes. So that's about chaos engineering and cloud native chaos engineering, why we wanted to introduce the Litmus project and how we did it using some custom resources and operators. That's the core of the project, and that was what the project was about for quite some time. These are some details about the resources and what they define. Probably skip that in the interest of time. Now, when we started thinking about Argo workflows is when we started getting feedback from people who are using Litmus in the community for doing chaos engineering. So there are complex scenarios where you would probably want to do more than one fault, and you want to stitch it together in a specific way, maybe multiple faults occurring in parallel. Things like you already have a degraded system, and then you suddenly have a pod that got evicted. Let's say all your nodes are running to capacity. How would you simulate that kind of a scenario, right? So you would probably need to create a chained failure. You had a fault, and then that injected something into your system, and it carried on for some time. You have another fault happening on top of that, which probably has disastrous results. Right? You might want to really check how you're tolerant to those kind of scenarios. So creating complex scenarios was one need. And then there was this need to validate application behavior during the automated experiment runs. Sometimes you're doing the fault injection and you're also peering into your observability systems. You're looking at the dashboards and you know exactly what's happening. But a lot of times the chaos runs as a background service. You just let the system go and inject failures at random times on random components, of course, within a control blast radius that you've predefined, but still in a randomized way. And you want to validate what's happened during the fault injection. You want to factor in the steady state validation as part of the experiment run. So being able to do that, so sometimes steady state validation is not a simple step. It could be a set of tasks that you do along with the fault itself. So that necessitates some kind of a workflow logic to be available. And many times fault injections on your pre-prod systems need to be done with some kind of load generation, some kind of stressful scenarios. You want to simulate production traffic. You want to run Locust or Vegeta or K6IO or any such load generation, just as your fault is happening. So that also probably needs us to run separate tasks. And there was another requirement where sometimes you need some pre-configuration before you run an experiment. Of course, clean up after the experiment. So these are all better structured as part of workflow. And always we would like observability. We want to visualize these steps running in your system. So these things sort of came in as the requirements and necessitated creation of workflows. And instead of building it out, we didn't want to reinvent the wheel. We wanted to look at existing options, and we chose Argo. Some of the reasons here, it's a Kubernetes native solution, which is also the philosophy of Litmus. And we had several executor types. We settled on K8s API because we had people running these workflows on different clusters having different runtimes. And the ability to define source artifacts, output artifacts, you get a lot of reports for the experiments that you run, ability to visualize, and a lot other technical reasons. And the other important factor was it is extremely well documented, has a great community as a CNCF project. And there were initial adopters of Litmus who were already using the CRs as part of an Argo workflow. So it happened to be an organic extension. We decided to bring it into the project and make it a formal part of the Litmus project. And as we started doing that, there were some parallel requirements that were emerging, such as the need for a dashboard or a control center that can manage chaos across a fleet of clusters. So we needed the workflows to be created and managed as part of this control center. And some of the practical challenges that we had, or some of the additional things that we needed to do while adopting Argo Workflows, was the ease of generating the workflows themselves. Sometimes the experiments can look pretty long like this. You have a chaos engine with all steady state steps and details on the services that you're trying to target. And there are different steps that you would do in terms of dependencies, installing some templates and running the tests, cleaning up, things like this. So for users, just as Flavio was explaining in the previous talk, wanted to make it a little simple. So how do you simplify the creation of these workflows by stitching together several faults? Each of these faults needs some tuning to be done. So we had to come up with a proper UX and a proper series of steps to be able to do that and make it simple for users. And typically with Argo Workflows, you have containers that run a task and you get to see the logs of the task that has been executed. But in the case of Litmus, the chaos engine creation, the CR creation is one of the tasks that would spawn a set of other pods which actually carried out the called business logic, something that we've referred to as secondary or generated pods. And we would like to see the logs of those as well. So that's something we needed to achieve. And because a workflow is now like a scenario, a proper scenario, test scenario, test cases and test scenarios are maintained in some kind of test management system. Mostly today people are using GitHub as well. So you need to be able to pull the workflow from source, ensure that things that are changed in your source are also reflected on your control center or the chaos center. So some kind of sync with the Git repositories for the workflows needed to be maintained. And the workflow status is actually the scenario status. And that needs to be factoring in the verdict of the experiment that we perform. So writing the right images that carry out the experiments and ensuring that you have the right failure or pass status of the individual nodes in the workflow is important. And sometimes when you stitch together several faults, you want to provide some criticality or weights associated with the experiment, depending upon how mature your infra or applications are to the workflows. You might want to execute the experiment all the same, but probably give it a lower priority than some other experiment. So how do you define these weights? And those are then used as part of some resilience score calculation in the platform. So we added some extra labels and annotations into the workflow. And basically, we were going to track metrics of experiments, and we wanted to know the parent workflow that actually ran the experiment. So there was some level of lineage that was added into the workflows to track the metrics. And so this was the instrumentation that we added to standard Argo workflows, and that resulted in what we call now in Litmus as a chaos workflow. And the Litmus chaos workflow is essentially an Argo workflow with some images being used as part of the steps to influence the result of the workflow based on experiment status and experiment result. And they are being stored in Git repositories and picked or sourced during the runs. So this is a summarization. So this is an architectural overview of the Litmus platform. I'll probably not spend too much time on it. This is basically the control center, which helps you to construct workflows. And you can run it in an execution environment. We call it as chaos execution plane, which happens to be the same cluster where you have the control center installed, or it could be a different cluster or different namespace. And there is a subscriber here, which takes instructions from the control center to apply a chaos workflow. Then you have the workflow controller that carries out individual steps in the workflow, such as setting up the dependencies, creating the chaos resources, and cleaning up, etc. And the Litmus operator picks up the chaos resource and carries out the fault business logic. So this is the structure that we are using. This is how Argo workflows are being used in Litmus. I'll probably stop at this point and let Shomo do the demo. Some of what we just discussed now will probably be reinforced or like become much more clearer when we see the demo. I just wanted to set some context here, and then we can take some questions. I think over to you, Shomo.
Thank you, Karthik. Hope I'm audible.
Yeah.
Let me share my screen. So yeah, so before I go into demo, I'll quickly give a explanation of the setup that I have here. So I'm running my local minikube setup here and have installed Litmus. So I've installed Litmus portal and all the other accompanying deployments like the subscriber, the event tracker, and other operators that are required, including the Argo workflow controller in the Litmus namespace. So this is my control plane for the Litmus itself. And then I have a demo application called the Potato Head service that's running in my demo namespace. And this is basically a HTTP web server. So that's all that this is. It has a service with it, accompanying it. And I have a monitoring setup running on the monitoring namespace with Prometheus and Grafana and a black box exporter. So if I open up the Litmus portal UI, I'll quickly log in and show the changes that I've made or the setup that I've gone through. So this is the portal that the homepage that opens up when you log in for the first time, and I'll give a quick run through of the options and menus that we have here. So on the left hand side, we see a navigation bar where we can see the different tabs and see the different options that we have here. So this is the homepage that comes in at the very beginning, which gives you an overview of the project that you're currently in. You have the option to switch projects if you are part of any other project, but currently I'm just a part of the single project. And in the home screen, you'll see the project, the workflows itself, the agents, and other project-related details itself. So this is just an overview or the summary of the project. Then comes the Litmus workflows or the chaos workflows, as we call it. So here we'll see all the workflows that we have run for the project, the schedules that we have in this tab. So these this can be cron workflows or single run workflows. In this case, I have only one single workflow that's just a single run workflow, as you can see here, and I've run it only once. And if I click on this, I'll get a beautiful visualization inspired from the Argo workflow visualization itself. So we can click on these items and see the logs and stuff, but we'll do it a little bit later on. So besides that, we have the chaos agents tab where we have where we get all the agents. So Karthik was talking about a subscriber that basically gets all the requests for your workflow runs and sends all the data back to the main control plane. So we see all the agents that are the subscribers that we have connected here. So currently I have just a single subscriber in my setup. You can go ahead and connect more subscribers if you want through the connect agent option. Then we have the hub where we basically collect all different types of experiments and predefined workflows that we have. So currently there's only a single hub, as you can see. This is the public hub that's available in the Litmus repo. But if you have your private hubs and if you have your custom experiments or workflows that you want to import directly into the portal, you can go ahead and create a new hub and go ahead with the flow. Then we have the observability tab, which is basically somewhat similar to Grafana itself. You can add in dashboards and have an integrated observability feature directly into the portal itself. But currently I have not set it up. I'll directly use Grafana for our demo. But yeah, besides the dashboards, you can also see inbuilt analysis or analytics for the workflows itself. So this is per workflow basis analysis. It's more useful for cron workflows. Over a period of time, you can see how your application or cluster is performing for the same workflow itself. So currently there's only one run, so there's not much to see here. And finally, we have the settings tab, which gives you a lot of options depending on whether you're admin or not. But in general, you have your own personal options to change, like the details, email address and name and stuff. Then you have team management options for the project itself. If you're an admin of the project, you get those options. Then you have user management options. Again, if you're an admin, then you can add new users and stuff. Then finally, the main important things that we are going to be talking about is the GitOps thing. So for each project, we allow a particular repository to be configured as a GitOps repository. So in this case, I've already configured my private repository that's here as the source, Git source. And just show how you can do it, I'll just edit it. So in this, to actually configure a Git repository, what we have to do is basically you have to provide the Git URL and the branch that you want to use as your source, and also add in the access token or SSH key so that the portal can write to your repository also. Because in our system, we not just sync from the repository itself, but we also write back to the repository. So in cases where you are creating a workflow directly from the portal will automatically sync that workflow into your configured Git repository. So that's why we need the access key. So I'll just leave it as it is for now. Also, we have the image repository option where you can specify, if you have a custom repository where you have all the runner images, the different helper images that we use in our workflows, chaos workflows. So you can do that by specifying custom values for this. But I'm going to use the Litmus open source ones that are already there, publicly available. But you can do that and you can use that in your workflows automatically. So that's also available for you. So going back to the main thing, that's the workflow itself. So in the Litmus Workflows tab, you get the option to schedule a workflow. And when you click on that, you are brought to this wizard where you are taken through a few steps where you can choose which target you want to run the workflow on and how you want to tune your workflow. So I'll just go through the steps and that'll probably be easier. So for example, I have only one agent or one subscriber here, so I'll select that as a target and move on. And then you can create your workflow. So we provide a few different options to generate your workflow. So the first thing that we have are the predefined workflows that are present in the hub, Chaos Hub, that we had configured. So in this case, I just have the single hub that is a public Litmus hub. So in that case, I have only 3 predefined workflows. And usually if you're just trying out Litmus for the first time, you might want to just run one of these workflows and see and test out the things, right? So if I click on one of these, and I'll just show you how it looks. So if I click on here and continue to the next workflow settings, you get the option to change the name and the description and basically a metadata about the workflow itself. And I click on next. And in this page, it's basically where you tune your workflow. Here we provide a pretty cool visualization or kind of a simulation of the workflow, how it will look after it's run. So here you can see how your workflow is going to perform as in how the steps are going to be executed and stuff. So here we can see that there's a series of nodes that are there, series of steps that are there, but at the end of the workflow we have 2 parallel experiments or 2 parallel steps that are being run. So if I want to change that sequence, I can click on edit and make some changes here. Like I can drag and drop in between these and get this visualization updated and all these actual workflow manifest itself updated also without actually having to edit the code directly. So that's mostly it for the edit part. But besides that, we also have options to toggle or edit our experiments itself. So let's say you have, in this case, I have selected a pod delete experiment. I can edit it, and this will provide me some tunables for the experiment specifically. So in this case, first of all, I get the metadata details like experiment name, the context and stuff. But if I click on next, I'll get the options for the target application. So here the wizard provides you with the settings to mention which particular application or particular deployment or particular resource you are trying to run the experiment on. So for example, the first one is the app NS. If I click on that, I'll get a list of all the namespaces that are there in my current cluster. So the portal is right now, the agent is right now running in cluster scope, so I have access to all the namespaces. But if you're running in, let's say, namespace scope, then you'll only be getting the access for that particular namespace. But in this case, I'm in cluster scope, so I have access to all the namespaces here. So I can, let's say, click on demo, which is the namespace that we are using for the demo. Then I can select on the app kind, which is basically the resource that I want to target. So in this case, I'll just select deployment, but you have other options like stateful sets, rollouts and stuff. And once you select that, you'll have to choose which deployment. So how we do that is using the app labels. So clicking on that will also give you a suggested list of app labels that you can use. So here what we are doing is we are fetching all the app labels that are there in that particular namespace for the particular resource type that was mentioned. So in this case, it's deployment. And in this case, we have the hello service as the particular resource. Sorry, the app label, right? So app equal hello service is the app label. And finally, we have the option to do some cleanup stuff. So in this case, we'll just leave it as retain. So retain is basically like after the experiments is run, it will keep all the resources, like leave all the resources on the cluster itself and not clean up. But we also have a global cleanup called revert chaos that you can toggle on the workflow itself. So it will clean up all the resources at the end of the workflow itself. So I'll just keep it as retain in this case for now. And then click on next will take you to options of probes, which is basically how you define your steady state hypothesis. In this case, we have a predefined HTTP probe, which we can add also, like we can add new probes if you want. And there's a proper documentation available for the probes, which we can share in the chat if you're interested. But basically we have like a few different types of probes. So if I click on this, you see the different types of probes that are available: HTTP, CMD, K8s, and PROM QL probes. So for example, the HTTP probe would be basically making HTTP request or to a particular endpoint that is specified. In this case, let's say the endpoint is already mentioned as this one. And this will allow, and then we can just check on different criteria. So let's say I have a criteria to check whether I'm getting a response code of 200, then I can just set it as this, and I need to set some other timeouts and retry values also. But the gist is that it'll the probe will basically make sure that that particular service is returning this particular response code that's expected from it during the experiment or after the experiment is run, whenever we want to actually run the experiment, run this probe. So to select that, like when the probe is actually executed, you can choose on the probe mode. So in this case, set to continuous, so it will go through throughout the experiment itself. But you can also set on start of the experiment or end of the experiment and things like that. So that was mostly it for the tuning part. Oh yeah, so I missed the tune the experiment section where we specify how long the experiment goes on for. So this section is specific to experiments itself. The previous sections were generic for all experiments, but this one will provide you specific options that you would be able to tune for specific experiments. So we have different options for different types of experiments. So like Karthik was talking about node level experiments and then network experiments and stuff like. So each of these experiments will have different configurations that you would like to tune. So you can add those tunables here and finish your workflow tuning and then continue to the next step. And this is where we finally select our weightages. This is a instrumentation that we have done over the Argo Workflows. So to get our resiliency score, we need to mention or we need to specify what weights or weightages each of the experiments that we're running in the workflow hold. So for example, in this case, I just have a single experiment, but if we had two different experiments, I could have different weightages for each of them. And depending on the success or failure of each of those experiments, we'll generate a resiliency score, which mentions how resilient your complete target application or this environment is, right? And that depends on the weightages. So if I have a weight if I've set a pretty low weight, then if this experiment fails, that does not affect your resiliency score too much. But whereas if I'm setting it to 10 and this experiment fails, then the resiliency score of your experiment or the workflow will reduce to 0, basically, because there's only one experiment here. So moving on to next, I have the options of scheduling, how I want to schedule it. So we have two options here. We can either go for a schedule now, which is basically just going to immediately schedule the workflow as it is on the target cluster. But we can also do a recurring schedule, which is basically going to schedule it with a cron job. So we are in this case we are internally using the cron workflows. So for the schedule now, we are just using the normal Argo workflows that are there, but for the recurring schedule, we are using the cron workflows for it. And here we are giving some predefined options like every hour, every day, every week, every month. And depending on which option you choose, you can also specify the minutes, the time, if it's every day or something. If it's every month, then you can specify the particular date of the month and then the time you want to run it on. And then finally, you can, let's say, like look at the overview of the workflow and then run it, right? But I'll not run this one. I already have a workflow that I've constructed specifically for this demo. So I'll just quickly go and take that up and I'll run that. And finally, we'll look at the visualization part. So yeah, so coming back to the workflow creation part again, we have the import option besides the workflow creation from the predefined workflows. And I can click on this and create a workflow here itself. So I'll just click on recent and upload my YAML. So this is the workflow that I've already generated for the demo. And this workflow is going to basically be running a Podlet experiment on my demo application. So the application that I had previously shown. So here's my application. So I'll be running a Podlet experiment on this application, but at the same time, I'll also be running a load test parallelly on it. And finally, we clean up the whole thing. So I'll just go ahead and schedule the experiment. And it takes some time to schedule it because it's now pushing the workflow to your Git repository first, and then it's going to execute it on the cluster. So now it's already executed, as you can see, it's running. While it's running, I can quickly show you that there was a recent commit to my GitOps repo that I configured. So here we can see that there's a commit made 20 seconds ago from admin@LitmusChaos. So if I click on it, and I'll see that there are a few other workflows also. These are the workflows that I ran previously, but the most recent one is 20 seconds ago. So this is the workflow that I executed just now. And we can see the whole workflow itself, the manifest of the workflow and the steps that are there. And just to show that what we are running. So in the steps, in the template section, we have the steps that we have mentioned. So the workflow is going to first install the experiment. Then it's going to, did I run workflow? 1 second. I think I ran the wrong workflow, but it's still fine. So yeah, so basically the workflow will show up here, but what we needed was a little bit different workflow. So what I'll do is I'll terminate the workflow. So the workflows, we also have the option to terminate the workflows directly from the portal itself. So I'll quickly terminate the workflow and run the correct one. So yeah, demos don't go well without glitches, I guess. So I just quickly select the proper workflow, which I think this is the one. Yeah, I think this is the one. Let me just verify. 1 second. Let me just. Okay, so this is the workflow manifest actually. Then yeah, this is the one. So I'll just quickly go ahead and execute it. Yep. Yeah, so now I'm running the correct workflow, which is actually going to run the Podlet experiment on the application and run the load test parallel with it. So again, going back to the Git repository, if I refresh the page, I'll see another file being created here. So which is the correct one this time. No, that's not. Yeah, this one. So yeah. Yeah, so this one is the correct one, as we can see. The steps are install chaos experiment, then we do a Podlet experiment, and finally we do the load test, which is running parallelly actually with the Podlet, as we can see. So it's running parallelly with the pod delete, and then we are just going to revert the chaos and clean up the whole cluster. So yeah, so going back to the visualization here. So I can see the experiment running right now, and the load test and the experiment has both started. And if I go back here, I should probably see, yeah, the pod has been deleted and it's starting up again. And here we can see the custom, yeah, the workflow pods that have been generated for the experiment itself. And clicking on the pod itself, we'll get a few details of the experiment. So these are the instrumentations that we've added apart from this tuning workflow tuning part. So we allow users to not only get the logs of the experiment, the Argo pod that's generating the experiment, but also the experiment pod itself. So in this case, we can see the details of the logs of the Argo pod, but then if we scroll down, we'll see logs from the experiment itself. So it would say that, started chaos experiment pod delete, and all the configuration details are also in there. So that's there. And in the load test one, if I go here, we'll see that the load test is running, and currently it's failing because there's only one instance of the application running. So, okay, so load test has actually completed, I think. Yeah, so we can see that the HTTP request failure is more than 25%. So all our requests that we're making is pretty much going to be wasted because the application is down due to the pod delete experiment that's being run here. So this is a weak scenario where our application isn't resilient enough to the experiment. So we'll see that if our hypothesis is correct. So we also have a HTTP probe here that checks for the liveness of the application while the experiment is running. So if the hypothesis is correct, then the experiment should fail, and we should have a failed node here once the experiment finishes. So let's just wait for a few seconds. Yeah, so the experiment has failed, as you can see. And going to the logs, we can also see the why it failed. So we can see the probe has failed for that particular experiment, and that's why the particular experiment completely failed. And besides that, we also have the chaos results. So this is also being fetched from the target where we are running the experiment. And here we can see the final experiment results that we are generating there. This is the actual Litmus experiment result resource that is being generated. So here also we can see the result, the probe status, which is mentioning that the particular probe has failed, and the verdict as mentioned as failed. So yeah, so we have completed the experiment. And besides that, what we can do now is we can also quickly run a more resilient scenario where we can see the particular experiment or the chaos workflow completely passing. So here, going back to the
hey, Shubho.
Yeah.
Yeah, sorry to interrupt. I think we're over time, and I hope the audience has got an understanding of how the Litmus workflows are being used in Litmus. So I'll probably we can stop at this point and take questions if any.
I have a question. This has been bugging me for a while, actually. I want to perform a chaos test where a service becomes unavailable. Does Litmus support that? Like another service like my Kafka, for example.
Right. So you're asking for the case where you're trying to make a service unavailable, Alex?
Yeah.
Did I understand that right?
Yeah, that's right. Yeah, basically my HTTP requests to that service fail, but I've actually got persistent TCP connections to it as well. So I've actually got open sockets which data is coming over. So it's kind of become unavailable midway during that TCP dialogue.
Yeah, I think we've had scenarios where that has occurred as part of these experiments. There are also some chaos experiments that are being built specifically to cause service unavailability, either by a 100% pod loss or by probably corrupting the service object, taking a backup and then just removing it from the system, kind of stuff. That is that something that you're referring to?
Yeah, that's the kind of stuff. Yeah, because I know you've got loads of different experiments inside the kit.
Yeah. I think there's also another question.
Oracle data, how do you do that?
Sorry, Alex, could you please repeat?
Say I'm running an experiment every day. How do you keep the history of that? Is that stored in a database? And
Yeah, so there is a Mongo DB database stateful set replica that's running as part of the control plane. So all these runs that you're seeing here on the dashboard are actually recorded there, and then there is an ability to run some analytics over it to see how your runs compare over a period of time. Maybe those runs have been executed against different builds or releases, or maybe the same experiment with the similar set of tables have been run across environments, QA, staging, on production, for example, and you get to compare them. It is stored in a database, you're right. Both the chaos results as well as the workflow details.
Does anybody else have any questions they'd like to ask? Okay, that's cool. So Shamu, Karthik, thank you very much for doing the presentation.
Thank you. Thanks for having us, Lex.
If people want to find out more, how can they find out more about LitmusChaos?
Yep. So I'm just sharing the repository here. It is at LitmusChaos/Litmus. That's the Git repository. And you can also join our Slack channel on the Kubernetes workspace. We are /Litmus on the Kubernetes workspace. If you're already there, you can join this channel.
Excellent.
The Kubernetes is a self-invite Slack workspace, so I'm pretty sure a lot of us are already there. So
I suspect so. Great stuff. Okay. So thank you very much for the presentation. What I'll do is, if you want to ask any more questions about this, I know we've had a lot of people had to leave for an 11 o'clock meeting, so you can obviously ask about that. And I'll be putting a recording up onto YouTube today or tomorrow for people to be able to watch the rest of this. Thank you all very much. I hope you have a wonderful day.
thank you. Have a great day.